of server threads ready to receive on the original channel. And this lifting is as simple as applying this congruence property for duplication and then just reusing the version we proved without the duplication. And again, there are infinitely many of these processes which in theory might all interact with each other and interact with the rest of the world, but that's all those worries have been encapsulated in the congruence property for dupe, and so we get a very direct way of handling this. I don't know if this kind of addresses the question about what loops look like here.
No, you didn't show the example of code that actually uses dupe in that way.
Oh, I mean a version that sends back to itself at the end, for instance. That's something you can do. Okay, so a loop that has an accumulator that is being modified over time can end with a send that another copy of itself picks up with a receive. That's the basic pattern for loops. But I don't have any examples of that laid out in this buffer already.
Or send A on a channel and cancel.
Okay. So to relate this back to the hardware domain, which I'm about to jump back into, to see why this is cool, imagine that P is the most highly optimized processor on the market, and P prime is a nice simple specification of what a processor should do. And imagine that dupe is the magical make into multi-core operator, and we can basically make that work, where you get many copies of your processor running at once, and in this nice, almost automatic way, prove that they all behave properly, where you can zoom in and just consider one processor at a time. All right, so I'm about to bring the screen back up and start talking about adapting these ideas to the hardware setting. Questions before I do that?
Yeah, it was related to this hardware setting.
Yep.
Infinite copies in hardware is hard to...
Yeah, we don't, so everything has to be finite in hardware, so we'll just do exponentiation with a known number of copies in hardware.
Well, there's never infinitely many. At any point in a computation, there's boundedly, there's some number. When is it's unbounded duplication? And in an infinite computation, that means there could be arbitrarily many floors. So it's a nice hardware.
Yeah.
Could I look at the dupe relation very quickly? Because it's...
You want to see the simulation relation behind it?
Yeah.
Sure.
It's pretty cool that you can do that without any preconditions or restrictions on the processes themselves.
I agree. I mean, it's basically what this says is two dupes are related if the bodies are related by the simulation that went along with the premise of the theorem, and then two parallel compositions are related if the left-hand parts, because recall the operational semantics rule for dupe spawned a copy to the left, so we apply the relation from the premise to the left-hand side of the parallel relation, and then we recursively check the same relation on the right-hand side. So every one of these P1, P1 prime pairs could be completely different, but the point is every corresponding pair between the two worlds matches up according to the relation. Any other questions before I show how to adapt this to hardware? Yes?
Is there any complications with the fact that you can send channels over channels?
In general, in this field, yes, there are complications, but I'm avoiding them here by saying everything's a NAT, and by not having a allocate new channel construct. Things are more complicated if you want to support that. Yes?
Is there any place in real system that this refinement is not enough to?
Yes. So sometimes the sequence of labels generated between the implementation and the spec is not quite the same. And you need to fix things up a little bit. And our library accommodates that with a variant of this refinement that allows rewriting of the trace of labels. That's just one example. There's a whole literature on different kinds of simulation that makes sense in different settings with words like stuttering that I'm just sweeping aside here. All right, so let me try to reclaim the blackboard. This looks familiar. So you might be wondering how this relates to the stuff that I'm erasing right now, or in general the world of hardware, where we don't want to assume that there are magic message passing channels and rendezvous and all that stuff. We won't have literally those features, but let me show you an example of what a module looks like in the BlueSpec language that is the inspiration for our framework, Kami. I'll also turn off that blue light if I can. I do this one. So, we're using a language called BlueSpec, which started as a research project at MIT before my time, and is today supported by a commercial company that sells CAD tools that will turn your BlueSpec code into, or push it along the path towards being silicon or running on an FPGA. And here's an example of what one unit of a BlueSpec program is like. Let's just say that this is analogous to the atomic processes up there, the kinds that didn't have any more parallel composition inside them. So what is a module? It's a lot like an object in a language like Java. So it has a bunch of private fields, which are called registers, and every register has a type. So I'll just draw a little overline or vector arrow here to indicate we have a bunch of registers, everyone has a type, and then we have a bunch of methods, very similarly to what we expect in popular object-oriented languages. Every method has for simplicity, I'll say exactly one argument of some type, and it has a return type as well. And then the body of a method is what's called an action. We'll see examples of actions shortly. Think of them like maybe Haskell programs in a state monad where the state is the registers or something like that. And then finally, the most interesting part perhaps, we have a set of rules. And it's almost like in BlueSpec we get to program by defining an operational semantics, and the rules give the atomic state changes that are possible. And the code inside one of these rules might call methods on other objects, and it's actually these method calls that will correspond to the message sends from above. So actually in the world of object-oriented programming in the early days, some of the first languages were described in terms of a message passing perspective on method calls, where a call to a method is a send, and then getting the answer back is a receive. And we're basically going to adopt that analogy for connecting to the label transition system style from up there. And so keep in mind, we're now doing hardware programming. All the types are finite. There are no function types. And yeah, so let me just briefly sketch how a set of rules like this gets turned into a circuit. So remember yesterday I talked about how there's a traditional workflow where we write some kind of meta program and then run it at compile time to get a flat version of a program. And then from there we translate that into what's called register transfer language. This code, think of as the result of the meta programming. And it doesn't yet look like register transfer language because it has these weird concepts of modules and methods and rules, but we can actually flatten this into a traditional circuit with feedback for state elements. So let's just consider an example of a system with two rules. BlueSpec provides the illusion that rules run atomically without being interrupted by others, though the compiler can sometimes be clever and find ways for rules to run simultaneously in the physical reality. So let's say we have a system with just one register. This box is standing for the register value at the beginning of one clock cycle. And then here's rule 1, which is some circuit that takes as input the register value and is going to compute the new register value afterward. Here's rule 2, yet another circuit standing for a different atomic rule. And then so rule 1 proposes a new value of the register. Rule 2 proposes a new value of the register. We can't keep both of them because then it looks like we got a concurrent execution of the rules. Rules are supposed to appear to run atomically, just like we're used to in operational semantics. So what we do to arbitrate between the two state changes that the two rules are suggesting is the BlueSpec compiler generates a circuit called a scheduler, which takes as input the register values and decides who gets to run next. And that scheduler is an input to this multiplexer. So this input basically says it's a bit. If it's 0, we'll take this value. If it's 1, we'll take this value. And then this feeds out into the new value of the register. And then we run this circuit again where the value of register in has been replaced by the value of register out that came through there. So this is one of the major ideas of how we can take this kind of code where many hardware people look at it and say, that's not hardware, go back to the ivory tower. But don't worry, there's a good compiler algorithm that turns this into the kinds of circuits that we're used to in hardware land. So any questions about this basic model before we move on? Yeah?
Is it worth going into a little bit of detail about what the scheduler is, what it does, how it's compiled or work?
Probably not. So in general, the rules can contain preconditions, and the scheduler checks which preconditions hold, and then applies some heuristics to choose to break ties between rules. Yes?
How does that compare to formalism like Unity, for example,
I don't know what that is.
or TLA?
TLA. How does it compare to TLA, which is temporal logic of actions?
So basically, the actions have enablement conditions as well, and you can have stronger or weak fairness on each action. So implicitly, you have a scheduler.
Okay, at a very high level, this is probably similar to TLA, but BlueSpec needs to be implementable in Silicon, and TLA, I understand, is more of a reasoning framework. So there are a lot of details linguistically that make this feasible with good performance, and that's probably the main delta from what you might know from TLA. Other questions? Yeah?
So the whole scheme with the scheduler and the rules is parameterizable in the number of rules that can be put together.
Yeah. It's all done silently by the compiler. The rules can be split across modules, and then we do a whole program compilation that orchestrates all of their execution. Yes?
So does that mean the scheduler is not sort of module locally generated separately for each module?
So there are multiple possible compilation strategies, and I'm not sure what the commercial BlueSpec compiler does, how modularly it manages to do scheduling. There are performance advantages potentially to a global view on optimization, but then it might make the compiler itself slower to run. So yeah, there's a trade-off there. Any other questions? All right, so let's talk about semantics of modules. I'll just write out a schematic version of the operational semantics that we'll use. It'll be a labeled transition system, just like up top. I'll use arrows between. So these R's with vector over arrows are standing for the values of the registers. For the moment, let's pretend we're just thinking about a single module, and then the states of the module are just the register values. I'll just draw the module name underneath the arrow in cases where it's not clear from context which module it is, and there's a label on top, just like up there. And a crucial thing, the output registers, we're going to make only the registers that were overwritten on this execution. We won't mention the ones that stayed the same. And that's going to be important when we get to the linking rule. Before I do that, let me say what goes in the labels. What's in a label? It's a list, or a set even, of a few different kinds of markers. We can have a syntactic marker that says a rule was run to generate this effect. Remember, rules are supposed to run atomically, so when we try to combine two transitions, if both of them include rules, then it's not sound to say they run at the same time. So we include a marker to record whether we used a rule yet. We have a budget of 1 rule per step. And then we had the same kind of labels before, except now I'm going to write them as method calls. So this syntax means I called method M with argument V, and it returned, I'll write a 1 here, with argument V1, and it returned V2 as the answer. And it also made local state changes inside the module I called, but those don't show up in the label. And dually, I'll have message receive looking labels that say, yes, someone else called my method M with argument v1, and I answered v2 is the return value, and I changed my state to reflect that. So in general, we can have multiple method calls. We can have a mix of incoming method calls, outgoing method calls, at most one rule inside the label, which records all of the aspects of this step that are relevant for communicating with other modules in the system. And then the crucial thing here is putting together two steps by two modules, or maybe even just one module. So
the N that appear below the arrow and in the list of labels,
yes,
they don't happen in the same namespace.
Same namespace.
The M under the arrow.
Oh, sorry, yeah.
Name and the M on the
Yeah,
right.
I'm reusing meta variables in a substandard way. I'll use a capital M for the module name. Then we won't have to worry about that clash. All right. So I have two steps of the same system, and I want to link them together in a generalization of what happened in this rule. So I'll say that works as follows. Okay, so I'm combining these two steps by using this little disjoint union operator on both the labels and the register updates that appear to the right of the arrows. And when I write a disjoint union operator in the conclusion, I'm implicitly including a premise that the things being unioned truly are disjoint. So we will reject linking of steps that, for instance, have the same register written by both sides. Because in general, in hardware, when you write a register, it works like a diagram like this. The new value has to flow into this one output position. If you have two competing writes, within a single cycle, you don't get that you write and then that value is installed and you can read it and generate a new value. There can only really usefully be one write of a register per cycle. So this rule enforces that we will not allow steps to run together if they're both trying to write to the same register. Similarly, by having a disjoint union operator for the labels, we won't allow two calls to the same method to happen in a single clock cycle. And I'll get back in a moment to why that's a good restriction. But a crucial property of this operator, kind of overloading it beyond the usual disjoint union meaning, is the kind of canceling behavior we see up here. So in particular, just to give one kind of schematic example, if I have a call to method M with argument v1 returning answer v2, and I try to link that as a label with an incoming call to method M with the same argument and same return value, then this combines to just an empty label. So when the two sides have the two sides of a call-return relationship, that call cancels out and no longer needs to be revealed to the world. This method has become an internal implementation detail of the larger module that we're building. And that is crucial for the modularity of all this. Question?
Can you model a one-to-many send with this?
One-to-many send could be implemented as a library on top of this functionality. It's not built into the semantics.